Okay, so first of all, let me discuss what is the uh, difference between a generative model and a discriminative model. Okay, because actually I was thinking the first point I should mention is that naive Bayes is a generative model, but then I should also discuss what is the difference between generative and discriminative models, right? So the first point is that, so we'll be discussing naive Bayes. We'll see why it's called naive and why it's called Bayes, right? So first of all, it is a discriminative model. Sorry, it is a generative model, not a discriminative model. Not discriminative. What does it mean? See, in any of the machine learning paradigms, what is our fundamental assumption? The fundamental assumption is that the data points that I have, let's say xi, yi, right? All of these data points are coming from some probability distribution or some joint probability distribution of x and y. And do we know this joint probability distribution? No, we don't know. We don't know this. Okay. And what we try to do, we try to gain some understanding about this distribution. Right? What do we do in logistic regression? If you remember logistic regression, has the logistic regression been covered, by the way? Hello? 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 Yeah, has this been covered, logistic regression? I mean, is it in a week before this or is it yet to come? Okay, okay. Okay, so this was not covered. Okay, no worries. So let me take the idea of linear regression. So in linear regression, what do we try to do? We try to understand this guy, expectation of y given x. This is what we try to understand in linear regression, right? And we say that, hey, this could be some linear function of my x, right? Or if x has more features, then you can adjust it accordingly, right? Or you can write it as some bias plus w transpose x, okay, if it's a vector. So what are we trying to do? We're trying to understand the behavior of, so in linear regression, the motivation or the primary focus is on understanding the behavior of y given x. This is what we are trying to understand. In generative modeling, in generative model or a generative modeling, we try to understand the behavior of the probability distribution of x and y, the joint probability distribution, right? Or it could also be the joint probability distribution, not the joint probability, the conditional probability distribution of x given y and the distribution of py. So if the focus is on y given x, then we say that it is a discriminative model. This is called a discriminative model. And if the focus is on the joint distribution x given y, or if the focus is on the joint distribution x and y, or if the focus is on x given y and y, then we call it a generative model. Okay, why it's called a generative model? Because once we have an estimate of this guy, we can sample from this distribution. So once we estimate this, we can sample more data points from p x given y. And how is this related? Because this will help us to estimate this, right? I'll just take a product of these two guys that will give me an estimate about this, right? I hope everybody knows that from conditional probability, right? And what do I mean by we can sample more data points from this? This means we can generate more data points from this, right? Sample or generate. And that is why it's called generative modeling. I hope the distinction is clear enough. So one good example of generative model is naive Bayes, which we will look today. So in naive Bayes, there are only few important concepts which you have to know. The whole idea about naive Bayes is on something called as conditional independence of features. Okay, which is a very strong assumption, but it's a weaker assumption than saying that the features are independent. Okay, we'll see some examples of that as well. But before that, let me tell you how to make a prediction using naive Bayes. So suppose you have features. Suppose you have this features, or let's say you have this data set D, which has a lot of features and a lot of targets xi, yi, I running from 1 to let's say n, and each xi is let's say in Rd. Okay, in Rd, or it could be some other feature space also. Let me just write capital X in general, and each yi is, let us say, member of some C, where C is a discrete set. Okay, what do I mean by a discrete set? It means C is equal to some C1, C2 up to Ck. So essentially what are we looking at? We are looking at some kind of a classification problem or a multi-class classification problem. Right? So this is a multi-class. Why multi-class? Because there are multiple classes. If there are only two classes, then we call it a binary classification problem. This is a multi-class classification problem. By the way, there is a very strong difference between multi-class classification and multi-label classification. Okay, I hope you know it by now, but yeah. So this is a multi-class classification problem. And if I give you a new data point, let's say x new, how will you predict y new for me? So what is y hat or what is y new hat? That is the first question, right? In linear regression, how did we predict? We tried to estimate a and b, and then you do a plus bx, right? That is how you did the prediction. How do you do the prediction here? So here, what you do is that y hat new equals, notice carefully, argmax over y, okay, okay, probability of y given x new. First of all, does this make sense? So I am predicting y new to be class, that class for which the probability is the maximum. So predict that class for which this this conditional probability is maximum. Makes pure sense, right? Now, I will write this as argmax again over y. Again, when I say over y, what do I mean? Okay, I should write y in C. Okay, let me write y in C, because y in C, y in C. Remember, what is my C? C1, C2 up to Ck. Okay. Again, I can write this as probability uh, x new given y times probability y divided by probability x, or x new, right? Why can I write it like this? Uh, Conditional probability or Bayes theorem, right? Bayes theorem. All good until now? Now I make an observation that hey, this denominator x new is not dependent on y. So I can very conveniently write this as argmax y in C probability x new given y times probability y. That's it. Why am I doing this? Because the denominator probability of x new is independent of y. And we are taking argmax over y, right? So you can ignore the denominator. Now comes the main part. Let us say that this x, okay, it has d features. D features. Okay, so let's say it has d features. What does that mean? That means xi is a d-dimensional vector, right? It could be in Rd, it could be in something other d, right? But there are d features. So I can always write x new as x new 1, x new 2, and so on, x new d, right? Because it is a d-dimensional vector, a d-dimensional feature. Okay. Now I can write this as, observe carefully, I'm writing it as argmax y over C. Okay. Py is as it is, probability of y. Right? Instead of x new, what I'm doing, I'm taking the product of all j from 1 to d, probability x new j given y. Actually, what did I do? I replaced this with this. Why I am able to do that is actually the fundamental assumption of naive Bayes. This is the fundamental assumption. See, whenever you have a model, you have an assumption, right? Based on an assumption, you build a model. What is the assumption for linear regression? The assumption is that the features and the target have a linear relationship between them, right? Again, there are some people from econometrics community have a different interpretation of linear regression. Okay, they say that the parameters are linear. That is why we call it linear regression. So for them, even a plus b x square is linear regression, by the way, because the parameters are linear. Okay, but that is a different story. But we'll focus on the idea that the features and the target have a linear dependence between them or a linear relationship between them. And what is that? That is our assumption. Similarly, in naive Bayes, our assumption is that, so this is the fundamental assumption of naive Bayes, and the assumption is that the probability of any x1, x2, dot 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 xd given y is same as probability of x1 given d, sorry, given y times probability of x2 given y, and so on. And this is called class conditional independence of features. First of all, I hope everybody understood why it's called independence of features, right? Why is it called independence of features? See, we are taking the joint probability to be the product of the individual probabilities. That idea comes from where? It comes from the notion of independence, right? Why class conditional? Because we are doing this when we are conditioning on this class. When we are conditioning on y, then we are able to do this. I'll give you an example of why this makes sense. Okay. Let us say you have a data set, right? You have a data set of people, and you have a feature called headache. Okay, you have a feature called fever, and then your target is unhealthy, healthy or unhealthy. That is your target. Okay, healthy or unhealthy. So these are my features, F1 and F2. This is my target Y. Or should I take something else? Let me take, instead of fever and headache, let me take something like headache and body ache. Okay, body pain or body ache. And instead of healthy, unhealthy, let me take fever. Okay. So first question, are headache and body ache independent? What do you think? Like, uh, I mean, a basic guess. What do you think? Are they independent? Like, do you think that if somebody has a headache, there is a higher chance of having a body ache? Anything like that? Any guess, guys? Okay, there is some message. Let me see. No, they're not independent. Okay. So someone says that they're not independent. Can you also give me a guess on why they're not independent? Why do you think they're not independent? Any guess? So the idea is that if they have fever, they may have both, right? They may have both due to the fever. Now let me go to the second question. Suppose I tell you that there is a person who has fever. So we know that the person has fever. It's known. Okay. Now my question is, are headache and body ache independent? Why? Do you think, suppose I tell you that someone has fever, uh, and if I tell you that the person has headache, do you think the conditional probability of the person having body ache also increases or decreases? No, I'm saying the conditional probability. So, okay. I'll explain it further. So the question is, so fever is known and headache is known. Okay, right? Uh, do you think that the person has headache or the person might have a higher chance of a headache, a higher chance of a headache due to some third factor, due to some other factor? See, what I mean by conditional is that you're already using the information that the guy has fever. That is there. But do you think there could be some other reason apart from headache and fever? For example, here we used headache and we tried to understand body ache, and you said, hey, no, it could be the case that the person might have fever, and because of fever, the person might have body ache. But here I am conditioning on both fever and headache. This is known. The person has fever is known, the person has headache is known. Now, do you think that he might have a higher chance of, oh, I wrote headache again. This is body ache, by the way, of a body ache due to some other factor? What is your answer? It could still be no, okay, because I mean, it could still be yes. So it could be the case that there is some other factor coming into play, right? But the assumption that uh, naive Bayes takes is that they are not dependent, which means that when you know that the person already has fever, headache and body ache are independent. Now, the easiest or the simplest explanation of this is headache and body ache, headache. So whenever I say class conditional independence, always think about this example, okay? Headache and body ache might be related, might be, you can say, dependent, but only through, only through fever, and not any other factor, and not any other factor. This is the whole assumption about. So this is what I mean when I say that class conditional independence. of features. Okay, here what are my features? Headache and body ache are features, and the target is fever. Fever, yes or no? Okay, so here headache and body ache, this guy and this guy, they are features. This is my target. And this is what I mean when I say that headache and body ache are class conditionally independent. Is the idea clear somehow? I would say focus on these two words, only and not. Okay, they could be dependent. I'm not saying they are independent, but the only way they could be dependent is through having fever and not by any other factor. That is the fundamental assumption about knife base. Is the assumption clear though? And I am able to do this change from this red guy to this green guy because of the assumption of class conditional independence. See, if it is independent, then definitely it is class conditional independent, right? That is for sure. So let me also write that. Independence, independence implies class conditional independence, but the other way around does not hold. Okay. So you can say that independent is a very strong assumption, so it is impractical, and class conditional assumption is a weak assumption, or class conditional independence is a weak assumption, but it is less impractical. I'm not saying that it's very practical, but it's less impractical. Okay. So now what do we have to do now? Now our task has been reduced to understanding these two guys. I just have to understand how to estimate Py, how to estimate Py, and I have to do this how many times? I have to do it for all values in script C, right? For all the classes. Right? Again, I'm considering a classification problem here, by the way. And I also have to estimate these guys, right? And it turns out that in knife base, we do this by simple counting. This is what makes, so we do this by simple counting, which also turns out to be the MLE uh, of this maximization problem, or you can say the MLE or the maximum likelihood estimator of this particular problem. Let us look at an example. From the example, we will try to understand how to do this. Okay. Okay, so what is the problem here again? We have three features. So D equal to 3. It's a binary classification problem. So the script C that we defined is either 0 or 1. The features are F1, F2, F3. Ignore the Laplacian smoothing part as of now, and we have to find out what will be the prediction y test. And what do you mean by class conditional independence of F alpha? It means that the probability, the joint probability of the features taking these values can be written as the product of the marginal probabilities. That is the overall idea about class conditional independence of the features. Yeah, so in this case, ijk can be 0 and 1 only. But in general, it could be anything, right? It can take more values as well. But in this case, I, j, k are 0, 1. Similarly, L is 0, 1. Okay. So let us proceed to solve this problem. So what do we have to predict? Y hat is equal to argmax over y. Again, y in 0, 1. Remember the formula? We had the probability of y and then the marginal probabilities, right? Product of the marginal probabilities. So this has to be equal to the probability of y times, again, what will be the marginal probabilities? It will be the probability that f1 is equal to 1 given y multiplied with the probability that f2 is equal to, see, f1 is 1, f2 is 1 and f3 is 0, right? So f2 is 1 given y and probability f3 is 1, sorry, f3 is 0 given y. Okay. Okay. Now, I mentioned that you can actually estimate this by simple counting, right? Remember, for, for each y0 and y1, you'll be getting different values, right? So we have to do it twice. So we have to do everything twice. So let us do this twice. What is the probability of getting a 0 and what is the probability of getting a 1? Remember, in the data set, we have 3 ones and 3 zeros. What does that mean? That means the probability of getting a 0 is half and the probability of getting 1 is also half. Because there are 3 ones in the data set, there are 3 zeros in the data set. Equal number of zeros and ones, right? Okay, that is fine. What about this guy? f1 equal to 1 given y and f1 equal to 1 given y equal to 0 and y equal to 1, right? So you want the probability of f1 being 1 given y is 0. You also want the probability of f1 equal to 1 given y equal to 1. Now what do? You do basic counting. Out of the ones which are 0, out of the classes which are 0, how many of them are 1? 1 out of 3, right? So these are the classes which are 0. Out of this, only one of them is 1, right? Therefore, I can write this to be equal to 1 upon 3. Similarly, out of the classes which are 1, how many of them are 1? So these are the classes which are 1. In how many cases f1 is 1? Only in 1, right? So again, this is what? This is my 1 upon 3. Now same thing I have to do again. I have to do for this guy also. Again, there will be two versions of it. One is f2 equal to 1 given y equal to 0. f2 equal to 1 given y equal to 1. Again, what will I do? Out of the ones which are labeled as 0, how many of them have f2 equal to 1? Again, 1 out of 3, right? So this will also be equal to 1 out of 3. Similarly, out of the ones which are labeled with class 1, how many of them have 1 as the second feature? Again, 1 out of 3. So this is also equal to 1 by 3. Now we have one last guy to estimate. Again, there are two versions. One is f3 equals to 0 given y equal to 0. f3 equals to 0 given y equal to 1. Now observe carefully. When y is 0, how many of them have 0? None of them, which means this is equal to 0. Similarly, When label is 1, how many of them have zeros? 2 out of 3 have zeros, which means this is equal to 2 by 3. So now we have two probabilities to compare. What is the first probability? In the first probability, we will take this guy, this guy, this guy, and this guy, and the product of all, right? So what did we get? That y. So okay, what are we trying to predict ultimately? What is this guy though? Or uh, what are we trying to predict? We are trying to predict the probability of getting y equal to 0 given x test, and we are trying to compare it with the probability of getting y equal to 1 given x test. And what does the first one turn out to be? It turns out to be equal to 0. I mean, not exactly equal to 0, but it turns out to be proportional to 0, right? I mean, why I'm saying proportional is because uh, remember, we ignored the where is that? We ignored the denominator px nu, right? So that is why I'm saying it's proportional, right? It's not equal to 0, but it's, yeah, it's proportional to 0. Similarly, if you look at the second guy, probability y equal to 1 given x test, it is the product of this guy, this guy, this guy, and this guy. So what is that? Half times 1 by 3 times 1 by 3 times 2 by 3, which is uh, 1 by 27, I guess, right? Now, which one is higher? Definitely this is higher, right? So what is my prediction going to be? My prediction is equal to 1. Did I do anything special? No. Simple counting, right? I mean, the only thing you have to know is the breakdown. Is that you can write it in this manner. After that, everything is simple counting, isn't it? Is this part clear though? Any doubts? So now let us see what is the idea about Laplacian smoothing. Okay. So the idea is this. Observe carefully. Why did this become 0? This became 0 because of this one villain, right? There is this one villain which is 0, and because of that, the entire probability became 0. Isn't that a little unfair for the 0th class? Because just because there was no occurrence of f3 equal to 0 in the 0th class, we simply dismissed it and we said that it has 0 probability. And here comes Laplace smoothing. Okay. And what is the idea of Laplace smoothing? The idea is that we don't want uh, any py given x to be 0 due to absence of features, or you can say absence of feature values, right? Feature values in that class. So here what did we have? We had the absence of feature value 0 in the class 0, which is why the entire probability became 0, right? So what is the workaround? Okay, before the workaround, uh, let me tell you how we came up with this 1 by 27 or with the 0. So we did some counting, right? So we took the count of number of occurrences of feature I equals to 1, or you can say feature I equals to let me write it like this: feature 1 equals to I, along with y equal to 0, right? And we divided it by the number of occurrences of y equal to 0. So when I say hashtag, it's actually denoting the number of occurrences, right? And that is how we got this 1 by 2, right? How did we get, not this 1 by 2, this 1 by 3, right? f1 equal to 1 given y equal to 1. So what did we do? We looked at wherever f1 is 1 when y is equal to 1. So it's actually a count. We counted how many times the label is 1 and the feature value is 1, and we divided it by the count of number of times the label is 1. That is exactly what I wrote here, right? And what is this? This is my probability, or this is an estimate of the probability that f1 is I given y equal to 0. This is an estimate, okay? By the way, this is an estimate. Laplacian smoothing says that, hey, don't do this, okay? Don't do this. Instead of this, use this guy f1 equals I with y equal to 0 divided by number of samples of y equal to 0. Okay. Add some integer L, some positive integer in the numerator, and some positive integer L times uh, number of classes in Fi. L times number of classes in Fi. Okay, so it's not Fi, sorry, F1. Okay. So in this case, what will it be? It will be plus L by plus 2L, right? Because there are two classes for F1. What are the classes? 0 and 1. Right? But in general, this is the idea about Laplacian smoothing. In fact, okay, first of all, if L is 0, then what happens? Then we get the normal naive Bayes, right? And if L is equal to 1, then we get Laplace smoothing. This is a more generalized Laplace smoothing, okay? Generalized Laplace smoothing. Okay. So is the idea clear? So this actually is useful when you don't want any probability to go to simply 0, right? It will add these values and it will make it non-zero. Okay. Instead of the simple count, you're adding a number to the denominator as well as the numerator. Remember, this is the number of class in F1, not in Y. Okay. Alright, so until now we have been looking at features which are categorical, right? So some features can be continuous. Continuous, right? So for them, how do you determine this value? See, ultimately we want this value, right? This kind of a value. This is what we want ultimately. So let us say there is some feature f4 which is continuous, right? Then how do you determine the probability f4 is some value, let's say 16, given y equal to 0? How do you estimate this, right? The idea is, again, you come up with some assumptions. So some common assumptions are that the PDF, or you can say that this guy f4 given y follows some normal distribution or some Gaussian distribution with some mean mu and some variance sigma square. Okay. And the crucial thing here is that this mu and variance actually depend on y. So if there are two classes of y, you have two variants of mu1 and mu2, or mu y1 and mu y2, and sigma square y1 and sigma square y2. And then instead of this, you use the PDF. Use PDF instead of probability f4 equal to 16 given y equal to 0. Very straightforward, right? Now the thing is, how do you know mu y and sigma square y? That you estimate using the data. Estimate mu y and sigma square y using data, and that is something which you can already do, right? For mu y, you can take the sample mean. So you can take the sample mean of all data points for which uh, sorry sample mean of all data points for which the label is equal to y, right? This is what that means. You must have seen something similar during Gaussian mixture models also, right? Similarly, you can compute sigma square y as summation of all those, or let me call it mu y hat and sigma square y hat, because these are estimates, right? We can compute it similarly using the same idea. And for the variance, you do this minus whatever estimate you have had for mu y, uska square, right? Classic formula for sample variance, right? So once you can estimate using the data, you can obtain the PDF, and then you can replace the PDF in place of this entity. And once you replace it, you will get the final prediction. That's it. Okay. Very straightforward. We'll probably look at some question for this, but before that, let me make one more statement that naive Bayes is actually a linear classifier. So quite surprising, but it is true. Okay. Why is it true? Let us look at some example. Let us say, let us say you are having a binary classification problem. Okay. Okay. So my y is either 0 or 1, binary classification problem. Let me introduce some notations also. Um, Let me say that let me make it as I need to introduce some good notations. So I should use py for 1 for 5, 1 for x. Okay, I think 1, 2, 3 ij. Anyway, cool. Okay, so let me say and let's say x is a vector in in RD. Okay, or let me, for simplicity, let me take 0 1 D. So so that means x1 is either 0 or 1, right? x2 is either 0 or 1. So all of them are either 0 or 1, right? So the target is binary and all features are binary. So remember, this is an example which we had here, right? All of them are binary. Okay. So when would you predict 1 for a data point? So what is the decision based on? The decision is based on uh, whether, or you can say the decision based on a comparison of the probability y equal to 1 given little x divided by the probability y equal to 0 given little x. If this is bigger than 1 or bigger than equal to 1, then we say y is the 1 is the label, 1 is a predicted label, and if it's less than equal to 1, then we say 0 is the predicted label, right? So let me write it like this, right? Now what is this guy? This guy on the left, I can rewrite it as probability y is equal to 1 times probability x given y is equal to 1, and that is divided by probability y equal to 0 times probability x given y equal to 0, and this is greater than or less than equal to 1, thereby I make a decision, right? Okay, let us say, let me call probability y equal to 1, let me call this probability p. So naturally, what is the probability y equal to 0? 1 minus p, right? So I can simply write p by 1 minus p first, right? And then for these two guys, I can take the product of the marginal probabilities, right? And how do, again, I need some more notation. Let us write it, let me write it like this, that the probability that xj, okay, equals 1, okay, x equal to 1 given y is equal to 1, okay. So this is, I'll call this probability as pj, okay, or pj1, okay, and I'll call this probability as pj0. I can do this, right? Right. So this PMF, probability x given y equal to 1, what is that equal to? Okay, first of all, this is Bernoulli, right? This is a Bernoulli distribution. If you look at only this guy, this is a Bernoulli distribution. So you can say that probability xj is equal to 0 given y equal to 1, this is equal to 1 minus pj1. So what is the PMF? The PMF is equal to pj1 to the power xj times 1 minus pj1 to the power 1 minus xj, right? See, when pj1 is, when xj is 1, I'll have pj1, and when xj is 0, I'll have 1 minus pj1, which makes sense, right? This is my PMF. And this is happening for all features, right? This is happening for all features. So you have to take a product along j. So what will I have here? I will have product along j running from 1 to d, right? pj1 to the power xj 1 minus pj1 to the power 1 minus xj. That is divided by what? That is divided by, again, same thing. Same thing. The only difference being instead of pj1, I have pj0. One minus pj0 power 1 minus xj. Now I can rewrite this as p by 1 minus p. Again, observe carefully. The product I am going to rewrite as pj1 by 1 minus pj1 whole to the power xj, right, times 1 minus pj1. That's a product here, by the way, divided by. Again, there is a product, j running from 1 to d. pj0 divided by 1 minus pj0 whole to the power xj times 1 minus pj1. Is this okay? Now remember this 1 minus pj, oh sorry, this is 1 minus pj0. This is repeated how many times? D times. Okay. So I can write this as, finally, there is p by 1 minus p. Okay, that is good. There is 1 minus pj1 by 1 minus pj0, but that is raised to the power d because it's a product over d. And then you have product of j running from 1 to d. What do you have? You have, okay, you have pj 1 times 1 minus pj0, right, divided by pj0 times 1 minus pj1, and this whole thing is raised to the power xj. Remember, this is only where we have xj. In the other terms we don't have xj, right? But still, is it clear why it's linear? No, it's not clear, right? Let me write it again. Just give me a minute. Let me take it to the other frame. Again, to recall, what is this guy? This guy is equal to, this guy is something which we got by changing probability y equal to 1 given x divided by probability y equal to 0 given x, right? And if this is bigger than or equal to or less than equal to 1, accordingly we will decide whether the label should be plus 1 or 0, right? Now what I will do, this is same as saying log of probability y equals to 1 given x divided by the probability y equal to 0 given x. And then I can write this as log p by 1 minus p plus d times log of 1 minus pj1 by 1 minus pj0 plus, notice here carefully, summation of xj times log of pj1 1 minus pj0 by pj0 1 minus pj1, and again this j is from 1 to d. What is this? This is a linear function in x. This is bigger than less than equal to 1, right? Accordingly we will decide. So this is a linear function in x or xj's. That is exactly why. So so you can think about this entire guy, okay, this guy as b and this guy as the vector w, and then you can write this as w transpose x plus b, bigger than or less than equal to 1, right? That is why we say that naive Bayes is actually a linear classifier, okay. And here I have taken a specific case when all of them are binary, but even if all of them are not binary, still the same kind of an idea holds. Okay. Okay, that is why the separation is always linear in naive Bayes. Okay, so what is the idea? Consider a two class naive Bayes classifier. So again, y is 0 or 1, right? With feature f1 as binary, so f1 is 0 or 1, and second feature as Gaussian. See, they have used an assumption that the second feature is Gaussian, right? And they have given these estimates, okay? And then they've said if a test point has label 0, what will be the probability that the point is this guy? So what does it ask? Is it asking for? It is asking for the probability 0 0, which means f1 is 0, f2 is 0, given y is 0, right? And assuming class conditional independence, what can you say? You can say that this is nothing but the probability of f1 being 0 given y equal to 0 times, see, the second feature is continuous, so I'll use the PDF. So I'll just write f of f2 is 0 given y equals 0. What can you say about this first entity? See, it is already given. Look at this guy. In this guy, it is given the probability that f1 is 1 given y is equal to 0. But what we know that if I add it with the probability that f1 is 0, then you are going to get 1, right? So this term, the first term, is nothing but 1 minus 0.4, which is equal to 0.6. What is the second term? For the second term, we have to use the normal PDF, right? So it says if y is 0, then it is normal 0, 1. What does that mean? That means it is equal to 1 by under root 2 pi e to the power minus 1 by 2 uh, okay, so this is going to be 0 minus 0 by 1 whole square. So this entire term is going to be e to the power 0, which is 1, and then you're left with 1 by under root 2 pi. So this entire term will become 1 by under root 2 pi. So what is the answer? The answer is equal to 0.6 by under root of 2 pi. You can solve this and get it to get it as a decimal, right? Now let us look at the second question. It says for x test equal to this, what output would naive Bayes predict? Now this is what we've been doing for a long time, right? How would you predict? You have to do the comparison between y equal to 0 and y equal to 1. For y equal to 0, what do we have to do? We have to compute probability f1 is 0, why 0? Because this is 0, given y equal to 0 multiplied with probability f2 is 1.5 given y equal to 0, and then I have to multiply this again with the probability that y equal to 0, right? That is also there, by the way. Similarly, for y equal to 1, what I have to do? Probability y equal to 1 multiplied with probability f1 is 0 given y equal to 1, probability f2 is 1.5 given y equal to 1. Again, these are although I'm writing probabilities, I'll be using the PDF, right, for normal distribution, and I have to compare these two entities and see which one is higher, right? See, it's given the probability of y equal to 1 is 0.4. What does that mean? That means that this guy is 0.4 and this guy is 0.6, right? For F1, we saw that this guy is 0.6, right? And the other guy is 0.5. Why is it 0.5? Because see here, this is 0.5. So the complement of this is also 0.5, right? Now what about the third guy? For the third guy, you have to do a little bit of more computation. So for this guy on the left, we have 1 by under root 2 pi, 1 by under root 2 pi, and then e to the power minus half, right? 1.5 whole square, right? And on the right hand side, we have 1 by under root 2 pi, e to the power minus half. This would be 0.5 whole square, right? So if you, yeah, tell me. Come again. Where? Hmm. Yeah, so okay, so it will be like this. It will be 1.5 minus 1 divided by 1 ka whole square, right? But what is this? This term is just 0.5, right? So I just wrote it directly 0.5 whole square. Yeah, because here it would be 1.5 minus 0 by 1 ka whole square. See, the means are different. For y equal to 1, the mean is 1. For y equal to 0, the mean is 0. That is why here I am having a 0. So the whole term becomes 1.5 whole square. Okay. Okay, great. So now what do you have to do? Now it's again straightforward. So let's say you don't have to compute pi and all, okay. So what you have to do is take this entire term as capital P and take this entire term as capital Q. What can you say about P upon Q? What is this term? This will be 0.6 times 0.6 times, see the 1 by under root 2 pi will cancel out, okay. E to the power minus 1 by 2, 1.5 ka whole square divided by 0.4 into 0.5 times e to the power minus half 0.5 ka whole square. Again, you can simplify this and say this is 0.12. Okay, so this would be 12, no, 36 by 20. So 0.36 by 0.20, which is point, no, this would be 1.8, I guess. Is it? 1.8, right? The first part. 0.6 into 0.6 by 0.5 into 0.4 is going to be 1.8, I guess. Let me also check. I'm also not very confident about all this. Yeah, 1.8. And this is multiplied with e to the power minus half, or let me say half. No, minus half is fine. Minus half 1.5 ka square minus 0.5 ka square. Okay. Now you can compute this, okay, and you can see that if it is bigger than 1, so let me just compute it quickly. 1.5 ka square minus 0.5 ka square. Okay, that is 2. So this term is equal to 1.8 times e to the power minus 1. Okay, so that is 1.8 by e, and e is close to what? E is close to 2.78, right? So this entire term is less than 1. So what does that mean? That means P is less than Q. So the prediction is going to be y equal to 1 will be the final prediction. Why? Because the value of q is bigger than the value of p, right? Is it clear? Is the whole idea clear?